Alright, so our goal in this video is to discuss some properties of parallelograms. So let's start off by defining what a parallelogram is. So a parallelogram is going to be any four-sided shape. That's what a quadrilateral is. Quadrilateral's a polynomial with four sides. Okay, we're going to say both pairs of opposite sides in this quadrilateral need to be parallel to each other. So I'm giving you a picture up here of what that would look like. Right? We're claiming that the top and the bottom of the shape, which we call opposite sides, those are parallel to each other, and the left and the right hand side, those opposite sides, are also parallel to each other. If that's true, we would call this quadrilateral a parallelogram. Okay, so there are several important properties that show up when we're talking about parallelograms that we're going to go through. Let's start off with talking about what opposite sides and opposite angles are, because you're going to see these words show up a lot. So when I'm talking about opposite sides, they're kind of highlighted in this picture here for you. You can see that BC, the top of this picture, and AD, those are two sides that do not share an angle, right? This has two letters, B and C, and then the other one has A and D. They don't share a letter, right? So if I were to take a look at things that are not opposite sides, AB and BC share the vertex B, so they would not be opposite sides. But I could say that BC is the top, AD is the bottom. They do not share a vertex, so I would call those opposite sides. And I would say opposite angles is the similar concept, but they don't share a side with each other. So angle C, for example, is made up of this right-hand side, okay, and this top side, right? And so I would say that this is opposite with A, because if you notice, A is an angle that is not made by either of the two sides that I just highlighted. So I would say A and C are opposite angles from each other because they are created using completely different sides. They don't share anything at all. Okay, so that's what we mean when we talk about opposite sides and opposite angles. So what we're going to do is we're going to use those words, and we're going to throw out a few properties, and I'm going to prove one of them for you, and then you can use kind of similar processes to prove all the rest of them. So I'm not going to do it for the rest of them. So here's your first property. So the first property is claiming that if a quadrilateral is a parallelogram, then the opposite sides of that parallelogram will always be congruent to each other. Okay? So in this case, if they give us a picture like this and they're claiming this quadrilateral is a parallelogram, and they're showing us that with the picture by putting the parallel marks on the top and the bottom and the parallel marks on the left and the right to show me that opposite sides are parallel, then I can draw the conclusion that BC has to be equal to AD and that BA has to be equal to CD. Right? That is the new property that we can get. So we're going to actually prove this one is true, and then again you can use similar concepts to figure out that the rest of them are. So we're going to prove that this property is true by using what we know about proving triangles are congruent. So the only thing that they're giving us in this problem is that AB and CD are, that ABCD is a parallelogram. So this symbol right here is the parallelogram symbol. So I'm just going to say step one, okay, I have this parallelogram called ABCD. Okay, that's given. Because that is given, okay, I'm allowed to say by the definition of parallelograms that BC on the top, okay, should be parallel to AD on the bottom. The opposite sides are parallel, and by the same token, the definition said that all of the opposite sides must be parallel. So AB has to be parallel to CD. Okay, so I'm going to say my step two here is that the definition, and I'm going to use the symbol again, of parallelogram says that opposite sides should be parallel. So I'm going to go up to my picture and mark that. I'm going to say we can claim that BC and AD are parallel, okay, and that AB and CD are parallel, right? So that's just coming from the definition. So now I'm wondering, how can I use this definition? So what I did was I drew this extra line in here called the diagonal, right? And when I did that, I created all of these other angles, and more importantly, I created triangles, because I know how to prove a lot of stuff about triangles. We know how to prove using things like side, 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 angle, side, angle, all of those shortcuts, that two triangles are congruent. And then once I know those triangles are congruent, I can tell you a lot of information about the triangles, right? So what we're going to actually do is use the fact that these lines are parallel to try to show you that these two triangles are congruent to each other. So the way that I'm going to do that, okay, is I'm going to say, well, let's start off with the easy one, okay, that the middle line, the diagonal that I just drew, is a shared line, so that I can say that AC is congruent to AC because of the reflexive property, right? So the reflexive property, which we use POC, the reflexive property of congruence says that a line is congruent to itself, right? So now I need to figure out how to bring in some additional information. I'm not allowed to use the theorem itself, so I can't use opposite sides are congruent because that's what I'm trying to prove is true. So I'm actually going to use the angles that we created here, and I can say because angle 2 is pinned between AD and this diagonal, and angle 3 is pinned between the other parallel line and the diagonal, that those are actually going to be equal to each other. So my fourth line is going to be that angle 3 is congruent to angle 2. Okay? And by the same measure, I can actually say that angle 1 here is pinned between this parallel line and the diagonal. Okay? And angle 4 is pinned between the same parallel marking, right, the double arrow, and the diagonal as well. So angle 2 and angle 4 are congruent. So let me just angle 1 and angle 4 are congruent. Angle 1 is congruent to angle 4. And if we had to give these names using what we know about parallel lines, we would say parallel lines being cut by a transversal implies these are alternate interior angles. Alternate interior angles are always congruent when we have parallel lines cut by a transversal. So if you notice my picture now, I really have an angle, side, angle. So the triangles are congruent because of our shortcut. So I'm going to say step 5. The triangle on the top, which we're calling, it looks like ABC, triangle ABC is congruent to triangle, excuse my congruent symbol, okay, triangle, it looks like I have to call this one CDA, okay, and the reason for that is, okay, the angle, side, angle shortcut, okay, so I can use that, and now we're done, okay, we can say, last step, AB is congruent to CD, definitely, okay, so let's write that, AD is congruent to CD, and BC is congruent to DA. BC is congruent to DA. And in both of these cases, if I go back up to my picture, it's because they are corresponding parts of congruent triangles. And we have our friend CPCTC that says if you have two congruent triangles, then corresponding parts of congruent triangles are congruent. And so we're actually applying what we know about triangle congruence to create these properties of parallelograms, in this case saying that opposite sides in a parallelogram will always be congruent, and the real reason that that's true is because of CPCTC. Okay, so I'm just going to give you the rest of the properties. We're going to do one quick problem and we are finished. So your second property, okay, again we can prove this using parallel lines, but we're not going to actually do the proof, is that consecutive angles will always be congruent to each other. And in this case, to describe what consecutive angles are, so we can use this property, we're going to actually say consecutive angles are ones that are right next to each other. So if I was looking at angle B, okay, I would say B, if I traveled straight across the same line, B is right next to A, and B is also right next to C, and so I would say B is consecutive with C, and B is also consecutive with A. So our property is going to be that if we have consecutive angles, okay, that consecutive angles are always going to be supplementary to each other. And again, if you want to know why, the real reason is that same side interior angles between parallel lines are always supplementary. That's really what consecutive angles are. They are on the same side of this transversal, but they're on in the inside of the parallel line, so I would call them consecutive interior. So consecutive angles are the same thing as same side interior angles, and they always add up to 180 degrees. So I have lots of pairs of these. I can actually say, well, C plus D should add up to 180. C is also consecutive with A. With B. C plus B should add up to 180. If I consider A, I'd say A plus B should add up to 180. A plus D should add up to 180. So you see we have lots of different relationships coming from the fact that consecutive angles should be supplementary. Okay? So here's your next one. Opposite angles. We've already defined opposite angles. Opposite angles are always going to be congruent to each other. And there's lots of different ways that we can describe this. The most simple one is going to come from this fact here. Right? This one is saying that consecutive angles are supplementary. And we have a rule that says, for example, if I were to take a look at these two, okay, we had a rule that says if two angles are supplementary to the same angle, then they are congruent to each other. So if you notice, A and C are both supplementary with angle B. So because they're both supplementary with angle B, they have to be congruent to each other. And the same thing is happening with the other angles. I could take a look, for example, at these ones, okay? and say, look at this, angle C. B and D are both supplementary with angle C, so they have to be equal to each other, right? So again, we have this property that just says opposite angles. If I say talk about A and C being opposite angles, they are always going to be congruent. B and D are opposite angles, they are always going to be congruent. Okay, so here is the last property that we're going to talk about. So our last property states that in a quadrilateral, if you draw both of the diagonals, that those diagonals are going to bisect each other. Right? And so this is one where we can do some calculations directly. If I were to draw the diagonal in and say, let's go from A over to C, and let's go from B down to D, I know that this line here, which I'll call this one, right, X, right, BX and XD, the two segments that got created, are equal to each other. Similarly, AX and XC are congruent to each other. However, be careful. We cannot say that two segments that come from different diagonals are congruent. So if you notice, I used one dash for the segments that came from BD. I used two dashes for the ones that came from AC, just to indicate that, you know what, this little segment that came from AC is not necessarily congruent to the little segment that came from XD. They're only congruent on the same diagonal. They're not congruent everywhere. So you got to be careful about that. Okay, so here's our last problem dealing with the properties. We're just going to apply this idea of the diagonals bisecting each other to some algebra problems. Right? So if you take a look at my first example here, I'm saying solve the linear equations. Right? So this is claiming that I have a quadrilateral, right, with the symbol here, quadrilateral KLMN, right? And I can say that y plus 10, which is one segment of the diagonal KM, is got to be equal to the other diagonal, 2x minus 8, okay, so I can say these are equal. Okay, and by the same notion, I can say LP is equal to PN, so x is equal to y plus 2. Right? So this is a system of equations. If I'm looking at these expressions, both equations have x and y in them, so I can't solve either of them directly. But using system of equations, I can actually take this expression right here, y plus 2, go up to the first equation. Anywhere I see an x, I'm allowed to plug in y plus 2. So I'm going to say y plus 10 is equal to 2. And instead of writing x, I'm going to write what x equals. It equals y plus 2. Okay. So now I'm just going to simplify this. I'm going to distribute out the right-hand side so I can do some combining like terms. Y plus 10 is equal to 2y. Well, this is going to be 4. 4 minus 8 is negative 4. Okay, so I can find out what y is, subtract the y over, add the 4 over, and it looks like I get a 14. So y is equal to 14, and then it's very simple to go to this expression right here and just plug in the 14, and I find out that x is equal to 14 plus 2, which is 16. Okay, and then the problem below is the exact same thing, so I'm not going to do two of them. But you get this idea that we just need to remember that diagonals bisect each other and create two congruent segments, and we can set them equal to each other and figure out this type of algebra problem that involves setting them equal, and in this case solving using a system of equations.